Probably give it another minute or two. Okay, it's 11:01. We can start. So happy Thanksgiving. Happy American Thanksgiving. I had just a few things to talk about before we jumped into paper discussions, paper presentations. A bunch more people answered, and it looks like almost everyone prefers the final week of classes, but at least one person cannot do the final week of classes. And there's a split between live presentation versus video, and there's also a split between Q&A and poster, although leaning towards the poster. So what I would like to propose is the following. And this is a proposal, so I am expecting feedback on, yes, this is a good idea, no, this is not. So this coming Saturday, we know the peer feedback is due. So you've picked at least 2 papers that you're going to read and give feedback, and that's due on Saturday. And then I'm proposing that we skip next Tuesday, and then next Thursday, the final class of the semester, for the one person who can't do the week after classes, that person could present on Thursday. And if anyone else wanted to present on Thursday, they're welcome to do that as well. For everyone else, you have 2 options. So on Tuesday the 8th, you could submit a video, and then everyone would watch those videos before Thursday. And then on Thursday, if you didn't submit a video, you would do a live presentation and either incorporate questions during the presentation or have a Q&A at the end. If you did submit the video on Tuesday, then everyone have already watched that. And then all of those people who did videos could do kind of poster presentations. So more like a conference setting where you could go and hop in to see the different papers. What I was thinking is for everyone, whether you're able to attend Thursday live or not, you could go and watch the poster presentation. You could watch the live presentations and watch the videos, and then have at least, like we're doing for when we were presenting papers, have at least one thing you liked and one thing that could be improved. So that's a way to get a bunch of peer feedback on your presentation or on your project. And then that feedback, along with your final version of the project write-up, would be due on Saturday the 12th. So I guess the main thing is you can either do, let's see, here it is. So you could just get everything done on Thursday the 3rd, second to last day of the class semester, or you could record a video and do a poster, or you could do a live talk and class Q&A. So I guess the first thing I wanted to ask is doing reserving a 3-hour chunk on Thursday the 10th. Does that seem reasonable? I'm guessing since classes are over, you won't have many conflicts, but that might not be true. So if there were a bunch of people that couldn't make it, then that's kind of a non-starter. Okay, I'm seeing. So is silence is consent? If anyone is not able to make it, let me make this a concrete question. If you are not able to make it, could you say something in the chat or unmute? Sorry. Okay. So it sounds like at least for the people who are here, it sounds like that won't be a problem. So hopefully it's not. If you aren't able to make it on the 10th, just shoot me an email, and we can figure out how you can do everything asynchronously. Or if for some reason these three options don't work for you, let me know that as well, and we'll figure something out. Yeah, it does give you extra time to get things together. Okay, so I will then send out a poll where I'll ask people just to decide which of these three options they'd like to do for their group. And then if something isn't going to work for you, just let me know. Any questions or comments on this?
You said that the peer feedback is due on Saturday, but it said the 29th. I think the 29th is Sunday. Just to be clear, it is Saturday, right?
It is Saturday, and you are right. Saturday is the 28th. And then I'm going to get you all the peer feedback on Sunday the 29th, along with my feedback, so that you'll have some time to incorporate that. Other questions or things I messed up?
So is the final draft due on the 12th or on the 18th? I thought, I think it was mentioned like last class, it was going to get moved to the 18th.
I thought it was going to be the 12th. Does anyone else remember the 18th? Okay, so I would prefer the 12th, because then that gives me a little bit of more time to grade. Of course, if something comes up, there's very weird times. If something comes up and you can't make the 12th, we'll figure something out. I know a lot of people have a lot of balls in the air right now, both in terms of school, but also in terms of a lot of personal stuff, that just between the pandemic and so if things are a mess in your life right now and you need extra time, just talk to me and we'll work something out. But otherwise, let's plan on getting everything submitted by Saturday the 12th.
Matt, for the video, what do you have, like a rubric of what you would like to see in it, or is it just kind of open to interpretation?
So I think for both the video and the live presentations, I do not have a real rubric, but that's a great thing that if I gave you some guidance, that would probably be useful. So I think your goal is, well, you want to tell people what you did, right? So you're going to want to explain the question or hypothesis you're testing, why that was interesting, or why it is interesting, and then hopefully you will have results and analysis done by then, so you can say what you've actually found. If you don't have your study completely wrapped up, you can talk about your initial results, and then so you say why it's interesting, what you're doing, what the results show, and then what next steps would there be. So for instance, I found this cool thing in the data, so I probably want to run a real study doing this that would measure this. That could be a conference paper. Or we thought this idea was cool, but the data shows the effect clearly isn't there, and the next step is to just ask a different question. Does that make sense?
Yeah, that was great. Thanks, Matt.
Yeah, you're welcome. Yeah, David.
Sorry, Matt. So quick question. So do we have to do both the 5 to 10 minute video and the live presentation, or is it one or the other?
No, one or the other. So I have a preference towards the video presentation, because that way we can watch them beforehand and Thursday won't be as long. But I saw a number of people did prefer to do the live thing. So I'm going to leave it to your groups to decide which you would do, which you'd rather do. Because if you do it live, then you can have a more back and forth with the audience. On the other hand, if you do the video, then you'll have the whole poster presentation where you can talk about your research in small groups. So I think there's pros and cons of each. All right. Let's see. Okay, so with that, I'm going to stop sharing, and I think we have 3 paper presentations today. So as we go, you can drop questions into the paper presentation Q&A in Discord. And also that this makes Discord a little crowded, but if you could also in Discord drop your at least one thing you liked about the paper or the presentation, or at least one thing you didn't like about the presentation, or one thing that could be improved in the presentation, or one thing that could be improved in the paper. So that way we can get some feedback to the presenters. So who would like to go first today?
We can go first. Can everybody see the presentation?
Yep.
Awesome. Okay. Leah, would you mind dropping the paper into the Discord?
Sure.
Thank you. All right, so our paper is called Human-Centered Tools for Coping with Imperfect Algorithms During Medical Decision-Making from 2019. So this presentation concerns the exciting world of pathology. I will try not to hold it against you if you all fall asleep. I'm sure nobody even noticed that there's two of the same image on this slide because it's pathology, who really knows? So our presentation, we're following the structure of the paper in general, and then we'll have a quick summary at the end, and then we'll take some questions after that. So the bulk of this paper concerns the topic of content-based image retrieval systems, which I actually hadn't heard of until now. So nowadays they're deep neural network backed, and the way it works is a pathologist will use a medical image itself as the query in order to retrieve similar images. These similar images are retrieved based on automatically learned metrics. So the reason that these systems are being made is they're good for teaching, for finding cases. They have excellent research applications, but in particular, this paper focuses on their diagnostic utility. So if you get a whole bunch of similar images, you can have points of comparison. It can assist you with filtering through diagnoses and triggering your brain to think of other ones. However, in going through the literature, at least that the paper references, there's very poor evidence that these are actually used lots in practice or that they even help very much. And this paper does go a long way towards helping that. So some of their goals. So they wanted to focus on the needs of pathologists, of their users, when they were building their system. But it's a difficult problem because the ideal concept of similarity is somewhat in the eye of the beholder. What aspect of a pathology image is going to be important? This may not be consistent across users, but it might not even be consistent across pathologists at different time periods or when they're thinking about or using different things. And so their solution is to give more control back to the user by allowing interactive refinement techniques. And so that way the users can focus on the type of capabilities that they want while they're using the system. So they created Smiley. This is actually what it is. It's similar medical images like yours, which I give the worst acronym award that I've maybe ever heard. It's hilariously bad, and I love that that's what they go through for the whole presentation. So as mentioned, it's a deep neural network-backed content-based image retrieval system. And some of their big contributions are these three novel features. So they allow pathologists to refine by region, so to focus on a specific region of interest, to refine by example. So when they look at the results and they see ones that they like, they can mark useful results and then find more like them. And then lastly, the most novel of these concepts is this refine by concept. So they can specify a clinical concept that should be present in the results. And I'll go over some of these a little later. So the way that the concept, the background and the related work of it works is that a deep neural network can produce an embedding for each image, which is treated like a coordinate in high dimensional space. Similar images or embeddings are close to each other in this high dimensional space. And directions in this high dimensional space can represent concepts quite well that are learned automatically. So for example, from the NLP world, the concept of male to female, you can see that there's similar directionality from king to queen as there is from man to woman. And this concept is preserved across many domains, including the pathological image domain. So I really liked how they focused on the user needs when they were designing this system. They didn't just set out to make something and then see if it works afterwards. They really had their users in the process from the very start. They had a multi-month iterative design process with 3 pathologists. They found that pathologists actually do seek out similar images from other sources when they're unsure of things, but typically this is from online sources or textbooks. The ideal images for pathologists will be ones that are most similar appearing, but that are across different diagnoses. What else could this look like is a question that they asked. They want to control which types of similarity matter. For example, they would say, I want to make sure that it's triggering on this gland. I want it to say, that's the thing. However, some features are regional, others are diffuse. Some things are more just like concepts. And so you can't always just focus in on a particular part of the image. They used images from a large pathology lab as well as image repositories to train their deep neural network. The query image is then fed through that neural network to retrieve the image embedding, and the 15 nearest neighbors in high dimensional space are then found. This is a screenshot of the user interface. Can you guys see my mouse? Okay, good. And this is the query image on the left, and then it would show the 15 nearest neighbors on the right. So for refined by region, demonstrated by the black box C here, the pathologist would crop a specific portion, and then this new cropped portion would be used as the query image to display the results. For refined by example, the pathologist would click on several examples from the results list, and then we'll use those to refine the search. And then the most interesting one, the refined by concept. So the way that they came up with this was in speaking with the pathologist and gathering their needs. Pathologists would say, for example, if this image had more fused glands, how would it affect the diagnosis? And so the concept of fused glands isn't something that's easily representable by just examples or by regions in images. And so, as I mentioned before, directions in that embedding space, they can represent semantically meaningful concepts. It turns out a simple linear classifier, a concept activation vector, can learn these directions. And so if you move from that query image in the direction of this CAV, you can find more images with that concept. So you can create a slider bar like this, where you can go from less fused to more fused, for example. Unfortunately, these concepts do have to be chosen by hand, however. And then what they did was they used 100 examples, and they had an expert pathologist go through each of those 100 examples for each of these concepts in order to get the classifier to work well. Each CAV then became a slider in the interface, as shown here. Something interesting is that a negative CAV direction doesn't correspond to a negative concept. So the opposite of fused glands isn't going to be unfused glands, which is what the pathologist expected to happen. It's no glands. And so what they did was they trained those negative concepts, the positive concepts and the negative concepts, in order to have that slider be meaningful in both directions. That wasn't the case for every example, but they did have to go back and do that. All right, I'll pass things over. I can stop sharing.
Oh,
I
yeah,
have a quick
just
question
share.
before.
Yeah, go ahead.
For that slider, when you said that they trained it for like the fused and then the unfused glands, and before they trained it for unfused glands, it would have stopped at no glands, like if you went farthest to left. How did they like do you know how they incorporate it into the new updated slider? Is it just like both sliders combined in the in between as the no glands option, or is there no glands option anymore in that slider?
There was no glands option anymore. They trained it on, like, they had pathologists just identify as negative the unfused glands and as positive the fused glands, and so the concept of no glands doesn't appear in the new slider.
Okay, thank you.
Welcome.
Scott, did you define what pathology studies? Maybe I just missed it or have already forgotten.
Oh, sorry. They look at slides, generally speaking, they look at slides of tissue under the microscope to make diagnoses. So they're often the ones that make the diagnosis of cancer. People make pretty big medical decisions based on pathologies, diagnoses. They're very high stakes.
Okay, so then these are all like tissue samples of different parts of the human body. That's
yeah, and
okay.
They weren't domain specific. They used a lot of prostate cancer because there's a lot of gray area and uncertainty in prostate cancer, but it wasn't limited to that. They really just used everything from their pathology lab. And they didn't go into very specifically exactly what they used and how they trained their deep neural network.
Okay, thank you.
So I will presenting the evaluation results and the user study. And so first is the evaluation results. So here is the tool evaluation, and the question they're asking is whether the refinement mechanism update results in the way intended. So they have a pathologist applied each tool to modify the research toward the concept they identified. So, and next, they will ask the other pathologists to look at the results and rate the percent of the concept. And they collect their rating and compare with and without refinement. So in short, the result is positive. So image contain a greater percent of the desired feature with refinement. So that means the tool is working. And they did an additional experiment on refined by concept. So the hypothesis is if the CAB had captured its concept really well, then the pathologist should be able to infer the concept. So they asked a third pathologist to identify the concept, and they said that the pathologist is able to correctly identify most of the concept. Okay, so next is user study. So here, the question they are asking is how refinement mechanisms are actually used in practice and their effect on user attitudes. So first, how does Smiley increase the utility for decision making? And does it affect the workload and trust? And the second question is how do pathologists use these refinement tools in their decision-making practice? So this is how the behavior of pathologists interact with the tool. And here is the measurements they use. So diagnostic utility, how useful the tool is, the example results, and how the mental support for decision making, the workload, the trust, future use, and overall preference between the two interface. So you have this Smiley interface and the traditional interface that just list all the relevant result and sorting by their similarity. So they have 12 pathologists participated, and first they will give the pathologist an online tutorial about the tool, and they will analyze 6 prostate images. And finally, they will have a post-study questionnaire and interview with the participants. And the task was not trivial, so they choose some really hard images. The pathologist will do 3 trials for Smiley and 3 trials for conventional version. So here's the results. And so we can see the orange is Smiley, and it shows a better orange, better rating overall. So, sorry, I'm in a full screen mode. So not actually if you guys really hear what I'm saying. Okay, so I see response. So I think things are working well. Now continue. And so in summary, so the user were able to retrieve more diagnostical relevant information with less effort with using Smiley, and had greater trust in the system and felt they were more likely to use it in clinical practice. And so at this point, you might want to ask about accuracy. So the author said that the focus of this work is about a refinement mechanism, not the diagnostic accuracy. So they didn't do an additional test about the accuracy. And they find no significant effect of different interface on accuracy and confidence. And next is the behavior they observe when pathologists interact with the refinement tool. So first, that they see that when the pathologists use refined by example, it's more when they instinctively saw images that might be relevant for what they care about. So it's more about instinction, and the refined by concept plays a more complementary roles to refine by example. So when they use refine by concept, they will think more systematically. And also for conventional interface, the behavior they can have is to sequentially scanning through the picture and skip over one that were irrelevant. So here is some behavior when pathologists doing their decision making. So first, they track the likelihood of their hypothesis, though they will first have a hypothesis in mind, and they iteratively search for more results to confirm their hypothesis. And the refinement tool can also be used to generating new ideas. So the concept slider can help raise awareness of unexplored territories. And some pathologists will use the crop tool to reduce problem complexity. So you might have multiple features that might be important in one image, but you can use the crop tool to crop one feature at a time. So you can investigate each feature one by one. And here are some behavior that pathologists do to cope with black box machine learning tool. So first, they attempt to narrow the semantic gap. So the semantic gap is what users are thinking is different from the machine is thinking. So they will emphasize relevant medical concept and reducing irrelevant examples to help narrow the semantic gap. And next, many of them will try to develop a mental model of the machine learning tool. So when a surprising result returned, many of them will try to explain what maybe some similar feature caused this surprising results. And finally, many of them will try to disambiguate the machine learning error from self-error. So the pathologist is able to preventively remove some variables and repeat the search to test what the error was come from the machine learning tool or from themselves. So from the above user study, we can see that the refinement tool enable user to customize assistant for their enrollment need without retrain the model. And second, the refinement tool can be used beyond improved research results. They can also be used for interactive tracking a diagnosis and building mental model of the machine learning tool. And also when we think in a broader range of human machine learning interaction, so human machine learning interaction has been traditionally used to improve algorithm. But in this work, they show that refinement mechanism can enable user to test, understand, and grapple with opaque algorithms. So this will suggest a new way of improve algorithmic transparency, which have traditionally focused on interpreting the algorithm to a human understandable way. So for the author's conclusion, so it might be helpful if we can think the machine learning based system as the augment of the human rather than replace the human when during decision making. Yeah, so suppose Scott.
Sorry. Yeah. Okay. You can just keep it on there.
Yeah.
I'll just use this slide just as a final summary. So the authors introduced the smiley system and forever burdened or gifted us with referring to it as the smiley system forever, which is great. As well as their most novel contribution here, which is the refined by concept kind of interactive mechanism. Another important thing that I think like a good contribution to this paper was the way that they involved their users in designing the system and in coming up with these techniques. And then also they did a really good job of testing their system with rigor. So they used controls, they used blinding, they used validated tools like the NASA TLX for measuring effort and frustration, Mayer's dimensions of trust for measuring trust with the system. Like I think they actually did a very good job. That's certainly the best job that has been done in CBIR in the literature. I'm not sure how it compares to everything else, but they did a really good job there. Well, overall, I do think that this paper adds quite a bit to the literature, but as the discussion in Discord shows, they certainly still had a lot of things that they could have improved. Questions?
Okay.
So I think we could ask a question or two, or Scott or Lehao could take one of the questions off of Discord, but I think it really should be probably one or two before we go to the next person.
We can answer questions just in the Discord, and the next person can go if we're concerned about time.
Okay, I think I'd lean towards doing that because I know some people do need to jump directly from this into another meeting afterwards. So why don't we stop screen sharing and let the next group go, which was David.
Yes, me and Raven.
Okay, I just put the paper and the presentation in the Discord. And I'm going to share the screen. Okay. Yeah, so I try to monitor Discord, but if I don't see your question,
I'll keep a lookout for even.
Yeah,
like
sounds
we
good.
We can do a swap kind of thing. Yeah.
Yeah, team effort. Okay, can everyone see the screen or am I sharing the wrong thing? Good, okay. So David and I are going to be presenting about this paper, Deep Q Learning from Demonstrations, that was done by a lot of people at Google DeepMind. I think there's like 14 authors, and this was published at AAAI in 2018.
And I'll point out that Todd Hester and I grew up in the same lab, and he's awesome. He's now at Amazon, and Mark Langto is DeepMind Edmonton.
Cool. Before we get into this paper, we're just going to talk a little bit about the motivation that the authors had in actually producing this work. So this came out in 2018, and the years leading up to this saw some really big achievements in DeepRL, such as the Atari playing agent. We also had RL doing motor control in this PR2 robot. And of course, AlphaGo beating Lee Sedol at the game of Go. So our DeepRL had these amazing achievements, but at the time we weren't really seeing any large-scale deployment in the real world, and still not really. So why might this be the case? Well, all of those systems had to take millions and millions of time steps to learn a policy and not have absolutely terrible performance. And this is great if you have a simulator of what's going on, like in Go or in Atari. But think about what would happen if you did something like this in the real world and you had a system like a self-driving car. This thing would be crashing and doing crazy stuff for a really long time before it actually learned how to properly navigate in the road. So something like this is completely unacceptable in the real world. Also, there might not actually be an accurate simulator for the application you want to apply your DeepRL algorithm to it. Like it might not capture all the details that might be relevant if you're actually going to implement this in the real world. So the main kind of question or goal that the authors have with this paper is that they want to ensure that DeepRL agents have good online performance before they actually start interacting with the real world. So that brings us to this paper, Deep Q Learning from Demonstrations. And to solve the problem that I mentioned on the previous slide, the authors propose pre-training from demonstrations from humans. And this pre-training process will let the agent have, or ideally let the agent have good performance from the get-go. And then once they're actually interacting with the real environment, they can continue to learn from their own self-generated data. And they, in the introduction, kind of market this or the use case of an algorithm like this for situations where you have demonstration data, but you don't really have an accurate simulator. But somewhat ironically, they decide to test their approach on Atari games, which does have an accurate simulator. So I'm not really sure why they chose that. I guess because it's DeepRL. But it would have been cool if they tried some sort of different evaluation context. So this paper builds on a lot of previous work and a lot of background. So we'll touch on that briefly. First, reinforcement learning refresher. We have our agent interacting with the environment. The environment gives the agent a state and a reward. The agent takes this information in, produces an action, which the environment takes in, and then will return a new state and a new reward for the agent. And it goes around and around. And the agent's goal is to find some policy which says for each state, what's the best action I should take? And how good a policy is determined by how much total reward or expected total reward you can get over your lifetime if you're following that policy. So how do you actually figure out what the optimal policy is going to be? Well, one way is you find out what's called the Q values for each state and action. And this is just a function that says, if I'm in this state and state S and I take action A, what's my total expected return going to be following a policy thereafter? And Q star denotes this function for the optimal policy. So once you find this function for the optimal policy, you get the optimal policy for free pretty much. You just take the actions that maximize this function in each state. So the next work we're going to talk about was DQN, which uses a deep neural network to estimate this optimal Q value function. And they call this a Q network. And the paper DQFD, or Deep Q Learning from Demonstrations, borrows a lot of the architecture from DQN. So here we have the agent and the environment interacting before, but there's a few additional parts of the system here. The first one is the replay buffer, and the agent will add transitions from the environment and its actions into the replay buffer. And it's just like a buffer that holds all this information. And then to actually train this Q network, which is learning these Q values, it'll sample mini batches of experience from the replay buffer and then update itself using gradient descent. And then the agent will use the information given from the Q network to choose its actions, and the cycle repeats. And here's a closer look at what this Q network is like. So it takes in, this is for Atari, it'll take in like the game screen, usually in grayscale or scaled down, and it'll run it through this deep neural network. And then for each action that the player could take, so move the joystick up, move the joystick down, press the button, a combination of those things, it'll return the value, expected value if you were to take that action. And then the agent can derive its policy using that information. So now I'm going to hand it over to David, and he'll talk a little bit more about the DQFD paper.
So yeah, learning from demonstrations. Next slide. So as a preface, as we heard before from Reven, DQN and most deep RL approaches assume access to like an incredibly large number of environment steps. And the reason why they need these environment steps is because they learn from the ground up. They have no priors, unlike humans. So let's say you're trying to learn an Atari game, like let's say Breakout. You have a prior of maybe even previously playing the game before, or even just like world priors of understanding, oh, the ball bounces off of a paddle, I know it's going to go in that direction next. So all of these implicit priors that we have when playing these games, our reinforcement learning agents have none of. And so I guess the idea that DQFD kind of brings forward is can we do this? Can we inject these priors into this agent through demonstrations? So just a general overview before we get into the nitty-gritty details of how it works. So deep Q learning from demonstrations is split up into kind of 4 steps. So the first step is where you pre-train with demonstrations based on an objective that we're going to talk about very soon. So after you're done with your pre-training, what you do is you act and collect transitions. You act and collect a transition and add it to your combined replay buffer. So your replay buffer contains both your demonstrations, well, not necessarily human demonstrations, but previous demonstrations, and also your own transitions that you generated. So after that, you update based on the same objective in the pre-training after sampling from this combined replay buffer. And then you basically repeat steps 2 and 3 until, you've solved the game or, you perform optimally. So next slide. So let's first talk about how pre-training is done and the objective that they use overall in DQFD. So as I said before, they create a replay buffer of demonstration data first. After that, you sample mini batches from the replay, and you basically try and optimize this combined objective of 4 terms. So it's this objective is essentially the same as the DQN objective, except with 3 extra terms. So let's go through them one by one, just to like get a feel for what our agent is actually trying to optimize. Next slide. So first, the Q learning loss, or the DQN loss, as they put it in the paper. So I'm sorry about the notation because I grabbed this from the DQN paper, and not from the DQFD paper. So there's a bit of a mismatch. But basically, the objective of the DQN objective, what it does is it's basically just least means squared error optimization between like the action value functions, or sorry, the Q values that you get from your model, and a target. So the target in this case is yi here. And so our target in this case is the what we call the bootstrapped a bootstrap TD target. And it's basically, oh, so what's the next reward I get plus the discounted max Q value for the next state. So there's a bit more theory involved as to why this is the target. And if you're interested in knowing it, please, shoot some messages. We're happy to explain. But for the purposes of this talk, it's a bit unnecessary, I guess. So all you have to know is that this is the target value, and basically it's going to approximate the true action value function. Not necessarily true action value function, actually. That's not completely correct, but something close to the true value function as you iterate through this algorithm and try and optimize this objective. So let's talk about the next objective, which is the end step return. So as we just saw before, the target was the next reward plus a bootstrap estimate of the Q value for the next state and whatever action onwards. So in DQFD, what they do is they also add an end step return. So they basically say, end steps into the future, I accumulate all of these rewards, and then afterwards I have my I have my bootstrap estimate of the state after that, and the value pertaining to that state in action after that. So basically, this is just an extended version of our one-step return, as we just saw before. And what this does is actually helps us with value propagation from our demonstrations or expert trajectories. So this helps particularly in pre-training because basically, if you think about what happens during a demonstration, not every single step in your, let's say, breakout game is going to give you a reward. And what you actually rely on is future rewards to propagate backwards to states that don't necessarily have rewards. So this end step return kind of helps with that propagation of future rewards back to, like, let's say that your start state for a breakout, where like your paddle is here and then your ball just leaves your paddle the moment your ball leaves your paddle, basically, because you don't know like what value you have based on just that reward alone, because there's no reward. So end step return, all you have to know is end step returns helps with pre-training by propagating back values, propagating future values back to previous states. Okay, now let's talk about our third term in our objective. So this is actually what they call the large margin classification loss. And what this basically does is help with imitation learning. So let's dig a bit deeper into that. What this loss does is it ensures the demonstrator actions in the states that you see in the demonstrations are at least some margin over unseen actions. So let's say in some state, the demonstrator will do left, or will take a left action. So what this loss does is say, okay, since the demonstrator did the left action, I know this is probably a pretty good action to take. So I'm gonna downweight all the rest of my actions and upweight my left action. And what this does is that, especially during pre-training, it ensures that you imitate your demonstrator to some extent. And we're going to see later on that this actually helps quite a bit in a lot of cases where rewards are extremely sparse in Atari games. And this imitation kind of learning helps a lot in getting returns for these kind of games. So as I said before, it's essential for pre-training on limited demonstrations because you have a lot less demonstrations normally than you do actual data. So our final loss.
David?
Yes.
What's that LAE, A term? Is that like estimated, like the estimated returns of the trajectory or something, or?
Let me get back to you on that. I actually haven't looked at the large margin classification loss too much.
It's it's called like the margin function. I think it just returns 0 when AE and A are the same and just a positive number otherwise. So it's supposed to put like the loss if it's not following the demonstrator's actions, higher than everything else by like just some offset pretty much.
Yeah, and it's probably something that you need to tune carefully, because if you make it too small, it doesn't do anything. If you make it too big, it could cause big problems.
Yeah.
Okay,
And,
so we penalize only if the actions aren't the same.
Yeah.
Yeah.
Okay,
Basically,
cool.
you're penalizing your Q value from being. Basically, you want the rest of your Q values to be lower than the one that the demonstrator took, and that's what this loss is. Sorry, that's what this objective is trying to optimize.
Could I interpret it as like a surrogate reward, maybe, or something? You want to add value? I don't know. Okay, never. Yeah.
I wouldn't call it exactly a surrogate reward, just because it doesn't act like a reward, if that makes sense. It more acts as a regularizer for your action values. Yeah, if you have more questions, please shoot us something on Discord, and we'll try and answer you. Cool.
Yeah. Okay. Thank you.
Awesome. Okay, and finally, our last loss, the simplest of all, just the normal L2 regularization loss. Since our pre-training data, our demonstrations are limited and quite a lot smaller than what you normally expect for deep RL. They add this L2 regularization to make sure that you don't overfit on this demonstration data. All right, and so taken all together, this defines our objective. And so after our pre-training step, we have our actual training step where we start taking, so once pre-training is done, our agent starts actually interacting with the system and taking steps and adding transitions to the same replay buffer. So demonstration data actually never gets replaced in this buffer, because normally you have a fixed buffer size, and after it gets filled up, the oldest guy gets kicked out or something. So in this case, our demonstration data always stays in this replay buffer and never gets kicked out, whereas our actual transitions might get kicked out later on once we reach that limit. So for prioritized, they also include prioritized replay in DQFD, and how they do prioritize replay. Basically, when you're sampling from your replay buffer, some samples, not all samples are the same. Some samples are better than others. And so how they prioritize the two types of data we have in our replay, so the one that comes from the actual agent and the one that comes from demonstration, is they have some small positive constants for their priorities for each of the two types of priorities. And you might weight like demonstration slightly more, just so you can sample from it more or something. Cool. So altogether, that's DQFD as a algorithm. And now let's talk a bit about how they evaluate this algorithm. So first, let's talk about the environmental setup. So as we mentioned previously, they evaluate using the ALE, the arcade learning environment, which is basically just Atari 2600, except for DBARL agents. So like we said before, it does all the regular pre-processing stuff as does DQN, as in DQN. So downscales and grayscales their frames, and then they frame stack 4 frames in a row as a state. And then they have a discount factor of 0.99. So this is all your regular stuff. If you want to know more about it, I highly suggest checking out the DQN paper. So they compare a few different baselines with this algorithm. So first, they compare the DQN algorithm. Next, the full DQFD with human demonstrations. And also, they do human demonstrations, and they also do, if I remember correctly, some teacher model demonstrations as well. They also do PDD DQN without any demonstrations. That just stands for Prioritized Dueling Double DQN. That was a mouthful. And finally, they do supervised imitation, which is basically just get rid of all your other losses except for that large margin classification loss, just to see how well imitation learning does. So a few notes and a few, I guess you could call them criticisms of the paper. So the authors performed what they say is what they call an informal parameter tuning, and use the same set of parameters over the entire set of games. So this is, doesn't make too much sense in our eyes, especially as like experiments. And they also use different parameters for different algorithms picked from a coarse search. So they don't really define what a coarse search is or what informal parameter tuning is, but sure. So also the results were averaged over 4 runs, which is also a bit, low number of Cs, but it's early days of RL, sure. Okay. And yeah, so they, in terms of the human demonstrations, they get human players to play each game between 3 and 12 times. And next.
Okay, so here are the main results of the paper on 3 Atari games that they decided deserved special consideration. These are Hero, Pitfall, and Roadrunner. Hero, you're kind of this little helicopter guy, and you helicopter around and blow up these walls to move around. Pitfall is about always moving right and avoiding these rolling logs that are coming at you. And Roadrunner is pretty much you're just trying to, I think you're the, what's he called? I think it's the Roadrunner. Yeah, he's trying to escape Wile E. Coyote. And yeah, you get rewards by escaping him. Anyways, so they showed their results for these 3 Atari games. On the x-axis, we have the training iteration of the network. And on the y-axis, we have the training episode return. And here, more is better on the y-axis. So first off from Hero, we see that DQFD outperforms both the supervised imitation and the PDD DQN by quite a large margin. It does, you can notice that it starts quite a bit higher, and that's because of this initial training phase. On Pitfall, which is a really hard exploration problem because there's really sparse rewards and you have to take a lot of actions before anything really, you know how well you're doing. So DQFD and PDD DQN both don't perform great. It's actually the supervised imitation that does the best because there's no notion of, you know, what's the best reward, and it's not actually interacting with the environment. It's just copying what humans would do for this game. But we see again that DQFD starts a lot higher initially than PDD DQN because of that initial training process. And then similar story with Roadrunner as Hero, PDD DQN and DQFD achieve similar performance after a while, but DQFD does start better because of that initial training process. And at the time of publish, the authors noted that these were the best performance on these 2 games. Something that we didn't really like about these figures is they kind of hide the pre-training process. It kind of shows like, oh, wow, DQFD has such better performance initially than PDD DQN, but it's really been training for quite a bit longer than the other algorithm. So it would have been nice if they would have included some sort of information as to how long the actual pre-training process takes. They also noted that there were 11 other Atari games where DQFD achieves higher results than any previously published DeepRL algorithm. But something else that we couldn't quite understand was the previous results are reported for the best agent on the best iteration, and it's evaluated for 100 episodes. But DQFD, the scores are taken over the best 3 million time step window, and then they're averaged over 4 seeds, but they're comparing these 2 things. So I don't know, it seems like an apples to oranges comparison here. I'm not really sure why it's done like this. Like, why not evaluate DQFD the same way these other algorithms are being reported? So that was some additional sketchiness in this paper.
Okay, so now we're going to go into some ablation studies and some additional results that they showed in the paper. So one interesting result was actually how often demonstration data was sampled for a given game for DQFD. And we can see here that this is the ratio between demonstration data and actual, agent data sampled. And we can see here, interestingly enough, both Montezuma's Revenge and Pitfall were sampled substantially more from demonstration data than all the other games here. And that's quite obviously due to the extremely sparse reward setting that both Montezuma's Revenge and Pitfall exhibit. And obviously human demonstrations will have more reward will have more rewards show up in their trajectory. So it makes more sense to propagate those rewards as compared to like the actual agent examples that don't show any reward and just, don't really do anything. That's why it's very related to why imitation learning works well with Pitfall as well. So next slide. And finally, some loss ablations. Basically, they showed that, so you can either take out your n-step TD loss or take out your supervised loss. They showed that the combination of all of them still works the best in terms of performance. And yeah, I mean, there's not much more to say about this. Cool. So Raven, do you want me to do the conclusion or do you want to?
You may as well.
All right, sure. So in conclusion, the DQFD apparently, improves on existing methods. So they did outperform the PDD DQN on the first million steps in 41 out of 42 games. But the PDD DQN still achieves higher episodic returns in 19 out of the 42 games at the end of training and has a higher average reward on 22 out of the 42 games, which is actually a majority. So over a best 3 million step window. So using that same metric, the weird metric that they use, instead of actually just evaluating your agent. So lastly, how does this relate to our project? So in our project, we also use demonstrations in our replay buffer to train a DQN-like agent on an entire game as well, breakout specifically. So while the DQFD agent puts all the demonstration data into the replay buffer in one go, we want to ask ourselves the questions, is this actually optimal? Like, if your agent is just starting out, it doesn't have any priors, and you showed some expert trajectories, is that really optimal? The gap between the two seems too big to jump to unless you do some form of imitation learning. So what we look into is what the benefits are of ordering our demonstration data based on agent performance or demonstration performance. So we look into how to order human demonstration data specifically to improve performance in a similar setting. And yeah. Thank you for listening.
Awesome. I think we should plow ahead into the final paper presentation, just for time reasons.
Sure, that would be us, I guess.
And also nice job, David and Reven, trading off one person talking and one person engaging on Discord. It's hard to do both at the same time.
So can you see my screen?
Yes, we can.
All right, so hi everyone. So we'll be talking about a paper titled Exchanging Advice and Learning to Trust in Multiple Agent System. So what is multi-agent system? So multi-agent system is simply multiple intelligent agents interacting with each other. And this particular paper addresses the topic of multi-agent systems where agents might be distributed through several physical or logical environments, and each agent have a degree of autonomy or freedom and may interact with each other in some capability. So the goal of the author or the paper is to create a set of techniques to allow agents to benefit from these characteristics. But it also mainly focuses on how agents can communicate with each other. So particularly it tries to answer the question of how can agents benefit from communication with their peers during the learning process to improve their individual and global performance. So naturally, we might ask, why is this communication between agents important? And one obvious way to have learning agents profit from communication with their peers is to exchange information concerning their experiences in the problem so that an agent can use that experience or information to better make decisions in the future. So the author and the paper tries to identify some of the questions or concerns with this exchange of information. The first being that what kind of information should agents exchange when the learning algorithms of their peers or agents are different. For example, say there is agent A and there is agent B, and if agent A uses Q learning and agent B uses evolutionary algorithms, for example, send the so the information when they exchange information, the information might not be relevant because they both are using different learning algorithms. Also, secondly, how does an agent select the best source of information? So for example, if there are multiple agents, to which agent should I go and seek for information that is more reliable and best information? And thirdly, how to produce good results given constraints like bandwidth, time, or computational power. Also, how can we be sure that the peer we are seeking help from is solving a similar problem and it provides useful information? Also, how should an agent decide when to seek help or when should it make its own decision? And lastly, how do we incorporate the information that we got from other agents into our own decision-making system? Or one of these solutions might be to use internal solution parameters, but the author mentions two main problems with this. The first being that agents do not know what learning algorithm peer might be using. So as we talked about, the information that we will get might not be relevant. Also, solution could be irrelevant if environment dynamics of agents differ from each other. So as an alternative, this paper introduced also a technique named advice exchange, which is a follow-up project or technique from their earlier work. So what is advice exchange? So advice exchange consists of giving the agents the ability to request information from peers and to learn from this information along with environment feedback. So it has So naturally, the key question lie in how we select, incorporate, and benefit from all this information that we will receive and how will we receive from the other agents. Also, as we talked about, knowledge should be gained based on the synthesis of information without extending entire solutions, because that would be just a waste of time and computational power. So in the following slides, we'll talk more about how this technique called advice exchange work. We'll talk about how the learning stages, how to decide to request advice, and to whom we should look for or as a solution or as a source of information, and how to incorporate the information that we will be getting. So one of the motivations that the paper mentions on how they get uh, the motivation for advice exchange is looking at how human team work. So for example, consider a human group of humans trying to solve a problem. So in the first step, we all try to explore solutions individually, and hopefully someone will find a solution within the group. And others will try to mimic the solution that one teacher or someone who found it. And first, we might ask for demonstration, and as we get more closer to solutions, we might work more individually, and we will try to find an optimal solution or improved solution, repeating step 1 to 3. So this is the motivation for advice exchange, and this process was transposed to the domain of learning agents in the following stages. So first, there will be individual exploration. Agents will not exchange information with peers, just like humans working individually in human group. This will improve the rate agents will explore different areas from each other. And secondly, agents will seek or ask for advice on all actions using the same advisor for a full epoch. So, and as a third step, agents will only request advice when the next action is unclear. So that paper calls it advanced advisee. And for the fourth stage, an agent might make its own decision and spend most of the time on individual exploration to improve the current policy, but it still might seek help from other agents. So Brad, or no, I'm sorry, so Spyros will be taking it from here.
Yeah, so there are two ways an agent can request advice, or criteria that it has. The first is by comparing its own performance to that of its peers, and this is what a beginner agent would use to request advice. And the other way is to measure the uncertainty of an agent's action. And so this is what more advanced agents would use. So the first approach, can you go to the next slide, please? So yeah, to compare one agent's performance to the other, the authors use a variable parameter called self-confidence. And this term is used to underrate or overrate its own performance. So self-confidence is increased whenever the agent's performance increases, or when it is similar to the best agent. Otherwise, the self-confidence parameter is decreased. And they define performance as defined here. So the performance at a given epoch n is a weighted average between the average reward during an epoch and the performance of the agent at the previous time. And they suggest this performance measure because they argue that it works well in environments which are dynamic, meaning that in a given state, if one agent takes action 1, and another agent takes action 2, it might result in a different reward and state. So for example, windy grid world, the wind has a factor that's out of the agent's control. Yeah, next slide, please. Yeah, sorry. So yeah, the other way is considering the uncertainty of the next action. So this is for advanced learning agents. And yeah, a way to do this is by looking at the Q values and comparing the variance of these estimates, so across each action. And with that, define an uncertainty measure and use that to request advice. And also another way would be to look at the best action and compare that to the worst action and use that as the uncertainty measure. So yeah, the next task for the agent is to decide the source of information. So in previous research, the authors found that the best advisor was not always the agent with the best performance. One situation this can happen in is where the advisor and advisee are in local environments that have different dynamics. And another possible reason is because it inhibits the agent to explore the entire state space. So early advising, it could reduce exploration or limit it to just a certain part of the state space. And so yeah, the authors present a trust parameter. And yeah, the decision of which agent to trust depends on this trust parameter, which is defined for each, and there's a trust parameter for each agent. And it's also dependent on this value E, which is the estimated performance of an agent in a given estate. So yeah, the agent would choose to request advice from the other agent who maximizes this trust times expected performance measure. And so this trust parameter is increased for all advisors that have contributed to the decision of an agent during an epoch when the average reward is higher, and trust is decreased otherwise. And to compute the estimated performance, which is the ES, all agents perform an unsupervised learning algorithm. And this allows the agent to define clusters of states and compute the estimated performance achieved for states in a given cluster. And these values are accessible to peers upon request. And trust can also be influenced by another agent. So in the paper, another agent can communicate with an agent and say, yeah, you should trust agent X, and it will update its trust values as if it had been a successful advisor. The paper didn't consider this, but they mentioned that an agent can communicate and say, don't trust agent X, and then they can decrease the trust value for that agent, but they don't do that in their problem. So yeah, there are two algorithms that are studied, Q-learning and evolutionary algorithms, and here we'll explain how advice is incorporated for these algorithms. So here we have the standard update for Q-learning. However, here, when an agent is advised to use action A as a response to state S, it will sum positive values and then increase them by some factor B up, and then for the values and for negative values by B down, and all other actions available at the state S. So basically, yeah, it increases the Q values of the action selected by the advisor or advised by the teacher. And so an evolutionary algorithm is defined as follows. So the solution parameters are interpreted as a specimen and its performance in a given problem as its fitness. So after evaluation of all specimens, the ones with the best fitness are selected for breeding. And the selected specimen are then crossed over and mutated to generate a new population. So the specifications for this particular evolutionary algorithm are as follows. So the genotype is the set of real valued matrices that correspond to the weights of an artificial neural network. And each specimen is evaluated during a certain number of epochs, so 3 in the study. And during the first epoch, there's no advice exchange. Furthermore, the selection strategy is elitist, so it keeps a number of the best specimen in the next generation. Mutation is done by distributing all the values of the parameters with random noise. And finally, the crossover strategy consists of choosing 2 parents from the selected pool and copying each node of the neural network from a randomly chosen parent. And so to incorporate information given, an agent will use back propagation with the advised action. Then the selection process will work on the specimens after they've been changed by the back propagation algorithm. So the advisors are evaluated by their trust quality product, defined by trust times their performance. And yeah, I'll hand it off to Brad now. Thank you.
Okay, I'll take over sharing.
Sure.
2 seconds here. Okay, you can see this all right? So to evaluate the performance of these agents, they only ran one experiment. It's using a problem called the pursuit problem, also known as the predator-prey problem. It contains 2 agents that act as predators and 1 agent that acts as the prey. They move around in a grid world where the prey is attempting to pursue and catch. Sorry, the predators are attempting to pursue and catch the prey. And the agents only receive a relative position of the prey based on their own position in the grid and other information. The accuracy of the state received by a predator depends on a visual range. It's an internal value. In the paper, it was only 3 grid spaces. The predator, beyond this range, it still receives a value for a range, but it's distorted by Gaussian noise. And the further away, the more distorted it is. Each predator on every turn only needs to make one decision between moving in either of the 8 grid directions or to just remain still. And the prey will always move away from the nearest predator every turn. If they're both equidistant, it'll pick one at random to move away from. At the end of each turn, the predators are rewarded with an individual and global component, individually just based on their distance from the prey, but globally based on a multiplier about how well its partner is doing, so that it's rewarded if it's working well together. As specified before, the predator agents use 2 main modes. There's Q-learning and the evolutionary algorithms, but they also have one that's just a simple heuristic that's always making an optimal choice, but in an individualistic nature. It never tries to work with its partner. And the experiment was carried out in 4 different scenarios. There's the individual scenario where there is 4 separate arenas running at one time, each with 2 predators and a prey as specified. In each arena, all the predators use the same learning algorithms and they never exchange advice. 2 arenas with evolutionary algorithms and 2 with Q-learning. Then there is the social heterogeneous scenario, which is the same as the previous, but agents can request advice from any of the 7 peers across the entire scope. Then there's the social heuristic, which is again the same as the previous, but there are 2 heuristic agents performing the same task that may be used as advisors. And the last scenario is the homogeneous scenario where all agents use the same learning algorithm at the same time. So to evaluate this, they ran 11 trials per scenario for 20,000 epochs with 150 turns per epoch. It remained in the individual exploration stage for 5,000 epochs, which was the stage where it would not request any advice. And they did 2 sets of experiments, one with a 10 by 10 grid and a 20 by 20 grid. So for results, kind of just summarize some of the most interesting ones here. Just a quick note about the visuals here with the graph. It's color coded, so the red is the results from the heuristic agents that just make the best individualistic choice. The green is the Q-learning agents, and the blue is the evolutionary algorithms. So in the 10 by 10 scenario, looking at the best result achieved by any agent in the area, the individual Q-learning was the most performant, but it did have a very high standard deviation. All agents trained in social scenarios performed much better, however. They all exceeded 0.205. As you can see here, these are all of the social scenarios right here. So you can see here that evolutionary algorithm agents clearly benefit from the advice of their peers because when they are on their own, they do not perform very well. The next set of results was just averaging all of the agents. In this case, sorry, 1 second here. Yes. So the best case in this one was the social heuristic Q-learning, which is particularly interesting because the heuristic agents can't be responsible for teaching good joint strategies because they never make decisions based on their partners. They only make an optimal move for themselves. And it can be seen here that the average performance of agents working in a group exceeded the capabilities of their best members quite easily. again with a very large difference there. And in the case of the 20 by 20, oddly enough, the individual evolutionary algorithm, one that had no advice, was the most highly performing result. They didn't really have many theories to explain why that was. It doesn't really match up with any of the existing hypotheses. And lastly, here it seems the Q-learning agents appear to have benefited from advice in all cases. Again, the Q-learning, all of them exceeded the individual notion. So the individual one is right down here, and these are all the different social situations here, here, and here. And lastly, in the case of the average performance in 20 by 20, once again, the individual agents are worse than the results of any of the scenarios by the social types. Yep, and the results in the heterogeneous environments are considerably better than the individual counterparts. I went a little wordy there. So, in conclusion, as the paper aimed to show, the exchange of information using advice exchange led to better average results. And generally, the homogeneous results were better than the heterogeneous results, suggesting that there is a benefit from using a diverse set of agents rather than a set of agents that all use the same learning algorithm. One key criticism that we were able to come up with was the fact that there was no accounting for how much advice the agents were requesting. Just simply that they could request advice was the only thing they presented. And for future work from here, we could look into application to more demanding problems, such as traffic control, perhaps. They could use learning stages to control the agent's learning parameters, to vary its exploration rates, and potentially looking at how to incorporate rendering unsolicited advice. So rather than having it to be an advice request, having agents give advice without any request. And I will turn that back over to Spiros.
Yeah, thank you. So yeah, in terms of project relevance, in my project, I argue basically that humans are maximizing utility instead of expected reward, and utility is a function of risk. So yeah, and I compare how humans of different risk levels affect the learning of an IRL agent. And so yeah, this ties into the paper, which addresses the question, how can an agent be sure a peer is solving a similar problem? So when a human is interacting with an IRL agent, there's a bit of a misalignment because the agent is wanting to maximize the return, while the human can be influenced by risk, and maybe they don't always take the best action. Yeah, and furthermore, it also, yeah, I haven't done this in my project yet because I've been splitting it by just, yeah, comparing one teacher at a time. But yeah, this paper presents a framework which allows multiple teachers and sourcing and how to source from them, so that I could try to incorporate into my paper. And finally, in my paper, it has yeah, the environment, it's similar to Windy Grid World, where even in the same state, an action can result in different outcomes. And so the paper suggests using their performance measure, which takes this into account and can have better results than just, yeah, blindly, I guess, following than just, I guess, either just using the return of a batch or an epoch. So yeah, that's it for our presentation.
All right, thank you guys. I'm going to suggest that when people have questions, please just drop them in Discord since we're already over time. But thank you to all the presenters, both today and earlier. I think this was a great, two of the papers I found really interesting because they're RL. I don't care about pathology at all, but that was actually a really cool paper too. So it's fun to see all these different viewpoints and different things that different people in the class are interested in. So thank you for doing that all. And with that, I'm going to turn off recording. And if anyone has questions, you are welcome to stick around.